Hi, this installment is our introduction to the notion of an inner product space. Perhaps one way to begin motivating this entire unit is to ask the following very simple question. Can we multiply vectors? We haven't really seen any instance of vector multiplication so far. We've seen vector addition. We've seen scalar multiplication. And that's about it. So we'd like to see to what extent we can multiply vectors. And to do so, we need to think carefully about what we mean by multiplication. For example, for real numbers, what does multiplication mean? Multiplication for real numbers is a thing that takes a real number and another real number and produces a real number. So it is, if you like, a function on what we call the Cartesian product of R with R, which sends two elements, say R and S, to their product, RS. So that's what a product on the real numbers is. We say this is the product of R and S. So let's see if we can generalize this and for an arbitrary vector space V, come up with some map from V cross V to R. We'll have a map like this and we'll call it an inner product on V. Right now we don't know what it is. We'll do this first in the very concrete settings of R2 and R3. And one of the most important morals of this story is that we'll see that this inner product that we define on R2 and R3 in a very technical and accurate sense encodes the geometry of R2 and R3. So we'll start our conversation, before generalizing to an arbitrary vector space, we'll start our conversation in this very concrete setting of either R2, the plane, or R3, three-dimensional space. The important point to make here is that we've been dealing with these vector spaces in many different contexts and in many different examples for several chapters at least now. But we've been dealing with them only as algebraic objects. For example, R2 as a set is the set of all 2 by 1 matrices with elements A, B coming from the real numbers. Now, it's more than a set, right? We know it's a vector space, so we can add the vectors in here, and we can scalar multiply vectors, R times A, B. And so this set has the structure of a vector space. But it has much more as well. Of course, we know that we can draw R2 as a picture, and each element, each algebraic element, column vector AB, corresponds to an arrow in the plane. And this arrow has geometric significance, and we have, for the most part, entirely ignored this geometric significance. In particular, this arrow has length. You can measure the length of it, and it has direction. That is, you can measure the orientation of the arrow with respect to, say, the x-axis, if you like. And these geometric properties of R2 have so far been entirely ignored, but that stops now. We will, with an appropriate product on R2 and on R3, essentially capture all of the geometric information about the vectors in these vector spaces. Let me briefly repeat the observation I just made. Any vector AB in R2 has two geometric properties that we'll focus on. A vector has magnitude and it has direction. The magnitude we measure as the angle between the vector and the x-axis. The magnitude we measure as the length of the vector, and the direction we measure as the angle between the vector and the x-axis. First, we'll discuss magnitude. If V is the vector with coordinates AB in R2, then we denote the magnitude of V as follows, and the magnitude of V is just given by the distance formula, square root of a squared plus b squared. You'll also often hear of the magnitude referred to as the norm of the vector. Magnitude and norm are in the literature the same words for the same notion. To record the direction of the vector, as I mentioned above, we could take the vector and measure the angle subtended by the vector and the x-axis, so this angle right here. We could do that, but we'll do something a little more general. What we'll do is we'll measure the angle between any two arbitrary vectors in R2. So we'll replace the notion of direction with the notion of, one might say, relative orientation. By orientation of two vectors, we mean the angle separating them. So suppose we have two vectors v and w pictured as follows. Let theta be the angle separating the two vectors. Then what we'd like to measure is this angle theta. And through an application of the law of cosines, as is described in the text, we can measure, we measure the cosine of this angle, and we find that it is given as follows. We find that the cosine of this angle is given by v1w1 plus v2w2 divided by the length of v times the length of w. Here, v1 and v2 are the coordinates of v, and w1, w2 are the coordinates of w. And there is an analogous formula for the angle between two vectors in R3. If v and w are vectors with coordinates v1, v2, v3, and w1, w2, w3 respectively, then the cosine of the angle theta between these two vectors is given by the following expression. And once again, we certainly haven't proven these formulas, but again, they are proven using the law of cosines, and that proof is straightforward and found in your text. And I'll certainly leave it up to you to go through that proof and to do a few examples where you actually calculate the angle between two vectors.